Hey, pre-calc 12ers. So we're going to start with just a little desmosing. What would it look like if in my table of values over here, I took a number like 1 and I multiplied it by 2, and then I multiplied it by 2, and I multiplied it by 2. What would my graph look like? All I did was I wrote out the powers of 2. And what I did is I basically made a geometric sequence by multiplying values by 2, 2, 2, 2, 2, 2. And you can see I got a nice little curve here. I could do something very similar where perhaps what I do is I actually take some values, and maybe I'll just erase these for now, but I take some values and I can go in the opposite direction. I could start with a number like, let's go 60, and then I could go divide it by 2, 30, 15, 7.5, 3.75, 3.75 divided by 2. Math started getting hard, so I'm just going to do it this way. 3.75 divided by 8, 3.75 divided by 16, and I can keep on going. 3.75 divided by 32, and maybe I'll just go one more for fun, but you get the point. And then, of course, what I'd like to do is I'd like to zoom in so it's a little bit easier for me to see. So if I do it this way, where I start with something big and I shrink it, I get a similar kind of curve. So what we're going to do today is we're going to look at what these curves are. We're going to look at the mathematical equation for a curve like this. We're going to give it a name and a whole bunch of other things. So let's have a look here. The title of today is 4.4, Graphing Exponential Functions. So the first thing we're going to do is we're just going to take a little second. We're going to segue out of geometric sequences into the world of exponential graphs. So let's just have a quick little look here. This is all pre-planned here. This is the paper version, although the Desmos thing I just did is kind of the same idea. So if we had a geometric sequence, 3, 6, 12, 24, and you plotted these on a graph, it would look like this. Okay, this time I actually wrote down the general equation here for any term. So the first term is 3, and then we multiply by 2. We do that at -1 times. If I wanted to think of this in terms of x's and y's, though, which I totally could, I can convert any term like this into y equals 3 times 2 to the x minus 1. So just instead of tn, I'm just going to say y. Instead of n, I'm going to say x. Okay. Here's my equation. And when I plot this on Desmos, it's not restricted to integers anymore, so it makes a nice curve going all the way through. Ooh, that was a nice freehand. That's my equation. One thing, just before we move on to talk about this, I'd like to point out, because if you're wondering if it's coincidence or if it's always true, it is always true that when we're talking about geometric sequences, this term here, which is the first term t1, is always going to be the coefficient out in front. R, which we can see going up here, we can see that we're always multiplying successive terms by 2, by 2, by 2. Then what that's going to do is that's going to be the base of the exponent. We're going to keep that in mind later because that's going to be quite useful. So the connection here is pretty obvious between a geometric sequence and a graph. It's going to make a nice little curving upward graph like this. All geometric sequences when graphed are going to have a similar curve. And what we're going to say is just a general statement. Any phenomenon, so anything you could measure where you've got repeated multiplication. So in this case, I was multiplying by 2 over and over and over. Repeated multiplication, the variable is going to be the exponent. That's going to be modeled by something called an exponential function. It's a function that has the variable in the exponent. Okay, so just before we get into the technical mathematical definition, let's just take a second, use a little common sense. Which of the following are exponential functions? This first one here, example 1a, you're going to recognize this as your good old friend parabola. Now, is this an exponential function? And the answer is absolutely not. Because if I was to do a little table of values like x and y, and I was to say when x is 0, y is 0, when x is 1, y is 1, when x is 2, y is 4, 3, and 9, and so on. I can't say I'm always multiplying by the same r. That's not actually happening. So r is not consistent. Oops, not consistent. Then this would definitely be This one here, y is equal to 2 to the power of x. Yeah, that is, because what we're doing here is if I was to make a similar kind of table of values, we could say x and y, and say 0, 1, 2, 3. We'd say 2 to the power of 0, well, that's 1, and 2 to the power of 1 is 2, and 2 to the power of 2 is 4, and 2 to the power of 3 is 8, and so on. And every time I can see that I'm multiplying by the same r, therefore it's exponential. So one thing we could kind of say is if r is constant, we have an exponential. If we're doing repeated multiplication, exponential. Okay, gotta think about how to spell that. Okay, this last one, the terms in the sequence 4, 2, 1, a half. And again, we can see that r is equal to a half, and then it's a half again, times a half, times a half, times a half. So yes. Okay, so this one was a yes, and so is this. So the condition for it to be exponential is we need constant values of r as we move from successive values of x, or we're multiplying by the same number repeatedly. Okay. All right, so moving on to the formal mathematical definition. The basic exponential function, which is our parent function, is going to be a function of the form f of x equals c to the power of x. C is just a number, it's the base of the exponent. C cannot be less than 0, can't be equal to 0 either, and it cannot be equal to 1. Reason for that just below. X is any real number, so you can raise like y is equal to 3 to the power of x. X can be whatever you want, because we can evaluate 3 to the 1, we can do 3 squared, we can even do 3 to the 0.4, if you remember, that would be like 3 to the 4 over 10, that kind of thing. We can do all that, so there's no restriction on x. X can be negative as well, we can also do 3 to the negative 4 over 10, that's fine too. So just keep in mind when you're dealing with exponential functions, it's going to be some number, some base to the power of x. X can be whatever you want, but the base has to have these requirements. And these are going to come up over and over and over, especially when we get into logarithms, which is very closely related to all this. So the base must be positive. The reason is, if we're allowing x to be any number, what is the value of negative to the 0.5, for example? Someone would say, well, isn't that the same thing as the square root of negative 4? That's equal to, well, can't do it. But you might make some argument that, well, isn't that like 4 to the 1/2, which could be the same as this? And this could be a thing. Couldn't we express this as like the 4th root of negative 4 squared? And that's the 4th root of 16. And then we say, well, doesn't that have an answer? Isn't that 2? Anyway, people get really confused with this stuff, and for good reason. It's not actually super well defined. So what we're going to say is we cannot have a negative base, and you can't have 0 either, because 0 to the power of anything is 0, and that's not going to make any kind of curve. Same thing with the base. The base can't be 1. You can't have 1 to the x, right? Y equals 1 to the x, because that's just going to be 1, 1, 1, 1, 1, right? If you were to actually graph this, it would just be a straight line like that if y is equal to 1. So just keep those conditions in mind. Properties of these exponential parent functions. I'm saying this part here, where's my cursor? I'm saying this part right here because this is just talking about the parent. When we start applying transformations, all bets are off, but for now, we can talk about just regular parent functions like a number to the power of x. They all share the following characteristics, regardless of whatever the heck the base is. So the graph of the y-intercept is 1, and we're going to call this a key point here because, well, this is pretty well the only one. The reason for this is very simple. Something to the power of 0 equals 1, as long as something is not 0. Because believe it or not, 0 to the power of 0 is not 1. It's actually poorly defined. All graphs have a horizontal asymptote at y is equal to 0. They're never actually going to touch, so all graphs are going to look something like whoosh. Okay? The graph has no x-intercept. There is no value of x you can pick that will make y is equal to 0. The domain is x is all real numbers. That's the same thing what we said up here. We said x is any real numbers. That's the exact same statement, so the domain is whatever you want. Then the range is, of course, y is greater than 0. So our graph's always going to be above the x-axis here, unless we start doing transformations. And let's just see a couple examples of some different exponentials. So this is color matched here, so y is equal to 2 to the power of x is this guy right here. You'll notice this point, they always pass through 0, 1, because anything to the 0 is equal to 1. 1/3 x is this red guy down here. He's going kind of a downward swoop. 0.1x, which of course can be expressed as, this is the same as like 1/10 to the x, is also doing a downward kind of swoop. It's not absolutely critical you get the, it's not really the slope, but let's call it the slope of the lines correct. It's not really a line either, but you get my point. What you're supposed to make sure you can do is identify the fact that these all go through 0, 1. They come really close to the x-axis but never touch it. They're defined for values of x, left and right, all the way to infinity and negative infinity. And if you want to get a little fancier, the bigger this number is, the steeper it goes. So, for example, 4 to the power of x is going to shoot upward more like, well, that's just terrible. I'm just going to pretend that never happened. There's no video evidence, right? Anyway, 4 to the x is going to go up like way faster. We don't even have to really guess at this, right? We can also use a bit of common sense. If it was 4 to the power of x, it would be going through the point 1, 4. So it would go up like that. Okay, it turns out it's actually kind of hard to draw these well. The other thing which is interesting is if it's going up really fast, it's going to go down really fast on the other side. So it's going to kind of do that sort of situation. So just be aware of that. Oh man, I can really handle that. Okay, so regardless of whatever the base is, we're getting the same characteristic shape. I guess I'll just label that. Okay, a couple words for you. We can define a graph as increasing or decreasing, and we can also call it having growth or decay. So what the conditions are for increasing is very simple. C must be bigger than 1. So that's like the base is bigger than 1. For a decreasing graph, C is less than 1. C is not allowed to be 0 or smaller, so it's between 0 and 1. And again, we can just look at what we just did, and we can see that this is a case where C is greater than 1, and we can see that it's increasing. It's this black graph up here going up. And if we make this less than 1, it's decreasing. These are still positive, but they're between 0 and 1, so they're both decreasing. Both these guys is going down like that. Little reminder for you, negative exponents are going to be important here, especially as we're talking about transformations. So 2 to the power of negative x is the same thing as 1/2 to the power of positive x. So when we're thinking in terms of transformations, a reciprocal base can be thought of as a horizontal reflection. So here's just a little comparison for you. Here's y is equal to 2 to the x. This and this, these are identical, right? And then this from here or there, this is a horizontal reflection, where all we did was we took the graph, and we flipped it over to the other side, and we made a horizontal reflection of it. So there's going to be two ways of thinking about graphs, especially when they're decay graphs or decreasing graphs. We can think of them as like 1/2, or we could think of them as to the power of negative x, depending on what your application is. Okay, so here's a little example. For each of the following exponential functions, determine whether it's increasing or decreasing, asymptotes, intercepts, sketch a graph, don't need to range. Okay, so here's a real simple one. Y is equal to x, 3 to the power of x. We can look at this and we can say that c is greater than 1, so therefore, I guess the answer for A, therefore it's an increasing graph. So all this is saying is our graph is going to have roughly this shape. It's going to be going up as we go from left to right. And that's just good to understand. B, determine the equations of any asymptotes and intercepts. Okay, so in this case, we're not doing anything weird. We're not doing any transformations. So we would say there's a horizontal asymptote at y is equal to 0. So you would draw that in. And you would say there is a y-intercept at 0, 1. So you put a point in there. Now C says sketch the graph. So if you're going to sketch the graph, you need a couple key points. My advice to you is do a little table of values. X, y equal 3 to the power of x. So we'll go 0. You know what? We're even going to maybe do a couple negatives. -2, -1, 0, 1, 2, 3, and we can keep going, but that's probably enough. So let's start with the easiest one. X is 0. That means 3 to the power of 0 is equal to 1. When x is 1, 3 to the power of 1 is 3. 3 squared is 9. 3 cubed, 27. 3 to the power of -1, remember, 3 to the power of -1 is the same thing as 1 over 3 to the power of +1. So that's just a third. And then 3 to the power of -2 is 1 over 3 squared, which is 1 over 9. So the way this graph is going to look is when x is, I'm going to space out a little bit, I'm going to go 1, 2, 3, -1, -2. So here we've got 1, 2, 3, 4, 5, 6. Okay, well this is going to end up terribly already, I can tell. In fact, I'm going to scale this slightly better. I'm going to scale this as maybe 2, 4, 6, 8, 10. At least I'll be able to get some of my points. As you can tell, it's going to be incredibly hard to get all of our points in on the same graph without squishing the smaller points together. So when x is 1, y is equal to 3. We'll plot this. When x is 2, y is equal to 9. When x is 3, y is all the way up to like 27. 27 is going to be like way up here somewhere, so I'm going to just label that 3, 27. Okay, so then when x is -1, it's going to be a third, which is going to be like way down there, 1 over 9, and so on. Okay, so we can sketch a graph going through those points. And we can make this go up and up and up. One thing I've noticed that people have tended to do is they've tended to forget that functions, they keep going, even if your table of values doesn't, even if Desmos doesn't. They do keep going here, so let's just maybe try and make that look a little bit better. But you're always going to have to put arrows at the end of functions where the domain is not restricted. Okay, so there we go. There's a graph. Y is equal to 3 to the power of x. Ta-da! You have drawn a beautiful exponential function. Let's state the domain and range. Okay, so for D, I guess I'll fit it down here. The domain is x belongs to all the real numbers, and the range is y is greater than 0. Fantastic. Okay, for question 2, we have 0.25, so we have to decide, is this increasing or decreasing? And we look at this and we would say c is less than 1, so therefore it is decreasing. So the general shape of this is going to go swooping down like that. B said, well, what did B say? Determine the equations of vast and twisted intercepts. Okay, well this is easy. This is still the same thing. At y is equal to 0, and we would say the y-intercept. Again, you can think about this, or you can just write it down, but it doesn't really matter because it's both the same result. 0.25 to the power of 0 is equal to 1. C. Now we have a couple options here. You can do it this way. Y is equal to 0.25 to the power of x, and you could go 0, 1, 2, 3, but I don't want to do 0.25 to the power of 3. So you know what I'm going to do? I'm going to use a little bit of intelligence here. I'm going to write this as 1/4 to the power of x, but I'm going to do you one better. I'm going to say this is 4 to the power of -x. You do not have to do it this way, but I personally like this a lot better. So that when I'm doing values of x that are negative, they're super easy to work out. So this is like 4 to the power of -2. That's 4 squared at 16. So when x is -2, y is 16. When x is 1, it's going to be -1, 4 to the power of -1. Okay, anyway, it's harder to say than it is to just write it down. That's 1, that's going to be 1 over 4. And you can probably notice pretty quickly there's a pattern to all of this. So similarly, we'll put in some points here. There's 0, here's 1, here's 2, and here's 3. Your scaling for this is going to be interesting. I'm going to go 4, 8, 12, 16 is going to go off here. But when x is -2, we're going to have that point. And then when x is -1, we'll be at 4. we'll go to that's about where 1 would be, and then the rest of it we're just going to have to estimate. 1 over 64, I can't even begin to get that accurate. So we'll draw ourselves a curve. We'll do the best job we can to try and get through the points and put arrows at the end, and I'm happy with that. So that is a reflection of 4 to the power of x. So that has that same decreasing. 4 to the power of x would go up like that. Okay, and then finally D, this is also very simple. The domain x is, again, all real numbers, range y is all greater than 0. Will this ever get more difficult? You bet. When we start throwing in some transformations, we will have to think a little harder about the domain and range, but for now it's very simple. Okay, question 3. Determine the equation of the exponential function in the form y equals c to the power of x. The reason why this is here is you can make some arguments that maybe it's been vertically stretched or whatever, but let's not worry about transformations for today. So what we do here to figure this one out, this is a little bit more of a thinky question. You can't just simply look at it and go, okay, it's obvious. This point here gives you basically 0 information because every single graph goes through that point. But these points here tell you something important. That was a mistake there. So what we're going to do is we're going to look at x, y, and we're going to just use a little bit of thinking. The answer might even be obvious to you, but I would like to make sure I can see it for myself. So y is 9, here 3, 1. We can't see it on the graph, but you can probably determine a pattern. So every time r is equal to a third, we're multiplying by a third every single time. Okay, so that does in fact confirm that it is geometric and it's an exponential function. So what we can do is we can use this idea that way in the beginning, I said, when you're talking about geometric stuff, t1's the coefficient out front, and r is the base of the exponent. We're not going to worry about this one too much, because right now, as I said, we're not dealing with any transformations. You'll notice this would actually be a vertical expansion coefficient, but we're not dealing with that right now. But this is the one we're going to focus on. R is the base of the exponent. So if you look at a table of values and you figure out that r is a third, what that tells you, this can therefore conclude the base is equal to 1/3. That's what we're repeatedly multiplying by. So we can now say y equals 1/3 to the power of x, and that should be fine. Or, if you don't like that, you can also say 3 to the power of negative x. Both are equally valid. Okay. Whenever we get an equation, you might take a second, double check the answers. So 0 and 1, 1/3 to the power of 0 is 1, 1/3 to the power of 1 is 1/3, 1/3 to the power of 2 will be 1/9. Yeah, sort of checks out. Okay, good. Moving on. Okay, and now finally an application of this. So if you don't think exponential functions are useful, you probably haven't been paying too much attention, because all you can hear these days is how the coronavirus is spreading exponentially, and it is totally an exponential function. I'd like to pick on something that's not so popular right now, because I think we're all tired of hearing about coronavirus. So another very common application is half-life. I think some of you have learned about this in science, but some of you might not have, or you were sleeping through class. So let's just take a little second and refresh our brains on what half-life is all about. If you have a certain amount of radioactive material, so here's a chunk, and it's all radioactive, emitting radiation outwards, a certain amount of time elapses, and we're going to call this 1 half-life. What happens is if you have this much, half of it on average decays, and it disappears. And then another half-life happens, so let's call this, I guess, maybe from the beginning, 2 half-lives. 1 extra half-life, but from the beginning, that's 2 half-lives. What's going to happen is half of a half is going to decay, so this is going to turn into half of it like that, and then you've got this much left over, and so on. So you start with a certain amount, and then you cut it in half, and cut it in half, and cut it in half. That's what radioactive decay is all about. Okay, so determine a function to describe the amount of carbon-14 remaining after n half-lives. So all we have to do is we simply have to understand here that if we say time or n half-lives, so half-lives, NHL, so we're just going to abbreviate that half-life, and we have the mass remaining. Remember, this is like time, so this is going to be our x variable. We would say 0 half-lives, 1, 2, 3, 4, and so on. So what we can do here is we would say the amount of mass after 0 half-lives would be 250. And then, yeah, that's right, I said 250. And then this is 125, and then divide that by 2, 62.5, and then this is 31.25, and then this is some kind of number I can hardly comprehend. I'm going to say it's 15.625, I believe. And what we're going to see is the amount is going to get multiplied by half constantly. So the way we turn this into a formula is once we realize what R is, we can simply say that the mass, which is a function of the number of half-lives, so I'm going to call it n, is equal to, we're going to start with a certain amount, 250, so that's like my T1 in this case, right? 250 is T1. So it's going to be 250 times R, which is a half, and then it's going to be to the power of. So now you just got to think about this. Do I want to make this exponent n, or do I want to make it n minus 1? Because I know when we were doing geometric sequences, this was always n minus 1. So what do I want it to be? So if n is 0, then I'll have 250 left. So this is going to be 250 times 1/2 to the power of 0. That would make sense. So I'm going to leave this as n because I don't want this 1/2 to count for when n is equal to 0. Only after the first half-life. So I guess this would kind of be like the first term. Okay, actually, you know what? Now that I'm thinking about this, we can maybe make an argument that that was T1. So there's two ways of looking at this. In fact, I might make the argument that this is T0 because it corresponds with 0 half-lives. So there's kind of two ways of looking at this. I think this is the simplest way, and I would say this is like T0. Sometimes people call it T0 for the starting value. People in physics will usually be comfortable with that. One way of doing it is this. If we wanted to call this T1, or I suppose it would be this number, that would be T1, then this would be M, and then this would be T1, and then we'd put it in the more familiar n minus 1 notation. Because if n was 1, then this would be 1 minus 1, which would be exponent 0, which would make this disappear, and we'd have 125. So kind of depending on which way you want to look at it, you can build the equation. The first way I did it, I would call just sort of the common sense way. The second way is relating this directly to geometric series or sequences. Doesn't really matter at this point. But they're both equally valid. Okay, so this was kind of like the, I'm going to call this like using logic or the table of values, and then this was kind of the geometric sequence way. And believe it or not, these are both the exact same formula. And if you really want to dive into why that is, you could say, well, 250 times 1/2 to the n. Well, that would be the same as writing this as, well, if we multiplied by a 2, well, let me just think of the best way to show this, but I'm thinking what we could do to turn this thing into this is we could multiply by 2 over 2, right? That's allowed in math. And then this would wind up being, let me just clean that up here. Right, all I did was I multiplied by 1, so that's allowed. If we multiplied this top 2 in there, that would turn it into 250. If we multiplied the bottom 2 into this one, we would get an extra 1/2. So the 125 would turn into 250, and then the 1/2 would get like an extra multiple of 1/2, and you'd wind up having 1/2 n minus 1 plus 1. But anyway, maybe that's a little more in depth than we need to get, so let's not worry about it, okay? Either one's totally fine. All right, so now the only thing we have to do is think about here, and I'm going to switch maybe to a different color. Instead of saying n half-lives, what about after t years? So let's call this t. So how many years have passed when 0 half-lives have passed? That's 0. After 1 half-life is passed, you have 5,730 years. Oh no, I'm going to have to do math again. Okay, so then after 2 half-lives, that's going to be what, 11,460, and then, okay, we're going to have to turn that into 17,190, I think. Okay, anyway, and then there's so if the question was now saying mass not as a function of the number of half-lives, but we actually had to think of it in terms of t years, we'd have a similar structure. We'd start with 250, and we'd still be multiplying by a half. But what would the exponent be in this case? Every time we go up by 5,730, we're multiplying by a half one time. So if my value for t, the variable, was 5,730, I would want the exponent up here to be equal to 1. So what I need to do is I need to write this in such a way that when the time is 5,730, my exponent would be 1. And the way to do this is actually quite simple. You leave the top as t, but you divide it by the length of the half-life, so that when time is equal to 5,730, the exponent equals 1, and I'm multiplying by half once to correspond with 1 half-life. And if the numerator was 11,460, then dividing that by 5,730 would give me an exponent of 2, which corresponds with 2 half-lives and so on. Okay, so this is just a different way of structuring the equation. It requires a bit more thought, but it's probably more useful. Okay, more on this later. There's a lot of different application questions that you can do that use a similar kind of thinking, but that'll come at a later time. Okay, so sketch the graph of carbon-14 versus half-life. So now I'm just asking, okay, let's do a graph of mass as a function of half-lives, not as time, but you could, versus the number of half-lives. So this is not really a hard thing to do. What we would most likely do here is we would say, here's n, the number of half-lives. Mass is a function of n. Remember, is equal to, I'm going to use the top equation from above because I think it's simpler, to the power of n. Okay, so after 0 half-lives, you're going to have, let's see here, you're going to have 250, and then 1, 125, 2, 62.5, and so on. Okay. So what's going to happen here? This is one situation where we've actually had a little bit of alteration to our parent function. Remember, this is a vertical expansion. So our key point here is not actually going to be at 0, 1 anymore. That's not going to be the case. What our key point here, in fact, let's call this 100, 200, 300. We're actually going to be shifting that up to 250. So our graph is going to go at 250. And we can therefore conclude, because of that vertical expansion, the y-intercept would be at 0, 250. So we're going to have to be on the lookout for that. And you don't want to get too hung up on the rules. We haven't shifted it up and down, so we're still going to have the same asymptotes, but that vertical expansion definitely changed the y-intercept. Anyway, the rest of the time here, we'll say 1 half-life, 2 half-lives, 3 half-lives. We'll go down to 125. This will be 62.5, and I think the next one will wind up being at 31.25 as well. One thing about this, the domain, let's not write x because we're talking about the number of half-lives. This will be greater than or equal to 0. This is because n is time. So in a realistic situation like this, we'll actually have to think about the domain a little bit harder. So we're just going to draw our graph going through these points. And we're going to draw it going something like that. Okay, so that's the lesson.